Choose common components. Wisely. Choosing the right tools and frameworks sets the foundation for a reliable, maintainable, and future-proof data architecture. Standardization reduces complexity. Using widely accepted and battle-tested components helps ensure consistency across teams and reduces onboarding time for new developers. Compatibility and interoperability. Select components that integrate easily with your existing systems and future tools. This prevents expensive rework or siloed data. Vendor lock-in consideration. Be cautious of overly proprietary solutions. Open source or vendor-neutral tools offer flexibility to pivot when needed. Community and ecosystem support. Choose components with strong community backing, documentation, regular updates, and a healthy ecosystem of plugins and integrations. E. Operational maturity. Go for tools with proven production readiness, good observability, stability, and known performance characteristics. Cost efficiency. Evaluate licensing, infrastructure, and operational costs. A cheaper component upfront may have higher long-term maintenance costs. Security compliance. Ensure components meet your organization's data privacy and security standards, e.g., encryption, access controls, audit logging. Skill availability. Pick tools that match your team's current or easily attainable skill sets, or plan for the training needed to adopt new ones. Data lineage and governance. Compatibility. Choose components that support metadata tracking, lineage, and governance tools to comply with regulations and internal policies. Decoupling and modularity. Use components that can be easily swapped out or scaled independently. Avoid tight coupling between services where possible. Plan for failure. Failures are inevitable. Architect systems to minimize their impact and recover gracefully. Implement redundancy. Use redundant data paths, distributed systems, and backup nodes to ensure availability. Monitoring and alerting. Set up comprehensive monitoring, logging, and alerting to detect issues quickly and accurately. Retry and backoff strategies. Incorporate retries with exponential backoff for transient failures to avoid overload. Circuit breakers and fallbacks. Prevent cascading failures using circuit breakers and provide fallback mechanisms for degraded but continued operation. Data validation and error handling. Implement robust validation at every stage and log failures with enough context to debug later. Disaster recovery plans. Design and regularly test backup and recovery plans for both data and infrastructure. Idempotent operations ensure repeatable and safe reprocessing of jobs to avoid duplication or corruption in the event of failures. Graceful degradation. Allow parts of the system to function even if others fail, e.g., stale cache instead of no data. Chaos engineering. Introduce failure scenarios intentionally, like Netflix's Chaos Monkey, to verify system resilience. Immutable data storage. Design data lakes and warehouses to store immutable raw data so you can reprocess or recover from any stage. Architect for scalability. A scalable data architecture can handle increased load, volume, and complexity without major redesigns. Separate compute and storage use services that allow independent scaling of compute and storage to optimize cost and performance, e.g., Snowflake, BigQuery. Use distributed systems design systems that scale horizontally by adding more nodes, e.g., Kafka, Spark, Hadoop. Partitioning and sharding partition datasets based on usage patterns, e.g., time customer ID, to parallelize and speed up processing. Data modeling for growth design schemas and pipelines that can accommodate schema evolution and increasing data complexity. Streaming for near real-time needs. Use stream processing, e.g., Apache Flink, Kafka streams, when batch processing becomes too slow or expensive. Pipeline orchestration. Use orchestration tools, e.g., Apache Airflow, Prefect, to schedule and scale pipelines in a manageable way. Elastic infrastructure use auto-scaling cloud services to match resource allocation with workload, e.g., Kubernetes, serverless. Caching for performance implement caching layers, e.g., Redis, materialized views, to reduce repeated computation and latency. Data lifecycle management, archive or delete old data systematically to avoid unnecessary bloat and reduce storage processing overhead. Benchmark and load test. Regularly simulate production loads to test performance limits and optimize before scaling issues become bottlenecks.